There, and welcome to tutorial 9 on trigonometry for the purposes of the Edexcel Core 3 Maths A-Level syllabus. In this particular video, I'm not going to be talking about any Core 3 knowledge. I'm going to be recapping and revising all the Core 2 trigonometric skills you required in order that in Core 3 we have the basic skills to work with. Now, let's take a look at what we needed to know for Core 2. Core 2, there was a fair bit we needed and we're going to use in Core 3. We need to know what sine, cos and tangent functions are. We need to know their graphs and various properties of their graphs. We need to know how to draw transformations of the sine, cos and tan graph. We need two very important identities and how to apply them and use them. And lastly, we need to solve various trigonometric equations. And here are examples of the type that we need to be able to solve. In this video, my aim is to go through all of this as quickly as I can so that you have a full understanding of all the basic skills required, and so that we can get Core 3 trigonometry off to a good start. Just keep our eye on the prize. This is what we need for the Core 3 specification. Everything in here requires the Core 2 knowledge and building upon that. That's why I feel this recap revision session is useful. Right. Okay, what do we know about sine, cosine and tangent from our GCSE knowledge? Well, what we knew then, if you have a right angle triangle and there is an angle inside it, one of the angles you are considering, say call it theta, you define the opposite side to be opposite the angle you care about, you define the adjacent side to be the one next to the angle you care about, and the longest side of the triangle is always opposite the right angle, and you call it the hypotenuse. At GCSE, we defined some ratios. We said that there is a relationship between the angle and the opposite and hypotenuse sides. In fact, sine theta, this function on our calculator, can be worked out by taking the opposite side and dividing it by the hypotenuse. Cos theta can be worked out by taking the adjacent side and dividing it by the hypotenuse. And tan theta can be worked out by taking the opposite side and dividing it by the adjacent. So that's how we defined sine theta, cos theta and tan theta at GCSE. Let's extend these definitions of sine theta, cos theta and tan theta so that theta doesn't have to be an acute angle. It doesn't have to be between 0 and 90 degrees, and this is how we would do it. Imagine you had a circle of radius r center the origin, and you considered you drew a line from the center to the circumference of the circle, and that's obviously of length r, that's a radius, and you constructed yourself a right angled triangle using that. This point here is going to be some point x across and y up, and sine theta in this case is opposite y over the hypotenuse r. Here's our formula. Cos theta is the adjacent x divided by r, and tan theta is the opposite y divided by the adjacent x here. So there's no difference in our definitions there. The only thing is here, in this particular circle, we can move the point around so that theta does not have to be between 0 and 90. Theta could be over here somewhere. And if it was over here, imagine we had this point here, and let's call it x2, y2, and say we had a line there. This would be theta 2, let's say. We can still define sine theta, cos theta and tan theta using these coordinates, and it would be the same. It would be x2, sine theta for example, would be y2 divided by r, cos theta 2 would be x2 divided by r, and tan theta 2 would be y2 divided by x2, where x and y now are positive and negative numbers because they are moving around the Cartesian plane. So it's a slight extension here. It's an extension of sine, cosine and tan to include angles not just between 0 and 90, but in essence any angle between 0 and 360 and onwards, or even going to negative angles if you define this to be theta to be 0. but we'll talk about that in a second. So a slight extension of our definition of sine, cosine and tan. Let's take a look exactly what I mean here. Well, here is a unit circle I've taken. So the radius here I've chosen to be 1 for ease, and theta is 0 here, theta is 90 here, theta 180, theta 270 here, and back to theta 0 or 360 here. So the centre here is 0, 0, or the origin, and I have found myself that if I take an angle of 30 degrees inside this unit circle and I extend the radius out to the circumference, I find myself having the coordinates root 3 over 2 and a half. And I can find sine 30, cos 30 and tan 30 using the above, i.e. sine of 30 is my y coordinate, which is a half, divided by my radius, which is 1, and that's a half. Cos 30 is my x coordinate divided by my radius, which is root 3 over 2 divided by 1, which is root 3 over 2. And tan of 30 is going to be my y coordinate, which is a half, divided by my x coordinate, which is root 3 over 2, and I would get for that 1 over root 3. Or if I rationalised it times top and bottom by root 3, I would get root 3 over 3. And so I can work out sine of 30 degrees, cos of 30 degrees and tan of 30 degrees using the coordinates here of x and y. So we knew that already because we could work with right angled triangles with an acute angle. However, now in the next picture, I have now got, I've still got a unit circle, but now I have got an angle that is bigger than 90 degrees here. It is 120 degrees in fact. And extending that out 120 degrees and drawing a radius from the centre to the circumference, I find myself at the coordinate minus a half and root 3 over 2. But I can still define sine, cosine and tan in this case here where the angle is actually obtuse. So sine of 120 degrees is still the y number divided by the radius, which is still the y number, which is root 3 over 2 divided by 1, which is root 3 over 2. Okay, cos of 120 is going to be the x number divided by the radius, which is minus a half divided by 1, which is minus a half. And tan of 120 degrees is going to be the y number divided by the x number, which is going to be root 3 over 2 divided by minus a half. And for that, you would get negative root 3. And so in this case, you have been able to work out sine of an obtuse angle, cos of an obtuse angle, and tan of an obtuse angle using these formulae. And we could keep going. Here's another one. I've gone even further here. We are now above 180 degrees. We are into reflex territory here. We can still work out sine of 225 degrees. And sine of 225 is the y number divided by the radius, which is minus 1 over root 2 divided by 1, which is negative 1 over root 2. Cos of 225 is going to be the x number divided by 1, which is negative 1 over root 2 divided by 1, which again is negative 1 over root 2. Or if we rationalise, by the way, in these cases, that would be negative root 2 over 2, and that would be negative root 2 over 2, multiplying top and bottom by root 2. And tan of 225 would be equal to the y number divided by the x number, which would be minus 1 over root 2, or negative 1 over root 2 divided by negative 1 over root 2, which would be 1. And you could check those on your calculator, and indeed you would find that these particular sine, cosine and tangent values are equal to what we have used from the unit circle. And taking our last one here, we have come all the way around here to 330 degrees, and we can say that sine 330 degrees must be equal to the y number divided by the radius, which will turn out to be minus a half. You can say that cos 330 is the x number divided by the radius, which is root 3 over 2, and tan 330 would be equal to the y number divided by the x number, which would be negative a half, divided by root 3 over 2, which would be equal to negative 1 over root 3, or if we rationalise it, negative root 3 over 3. And you could check these on your calculator and find that they are in fact right. So relating sine, cos and tan with an angle to the unit circle reveals for us how we can extend sine, cos and tan and how we can evaluate them. Okay, one tiny little thing to go back and mention here is that if we go back to the very start here, as well as this being, if this was defined as theta equals 0 line, as well as defining this as theta is 30, I could go this way and say that actually theta is equal to minus 330. And if we typed in our calculator sine of negative 330, we would get the same answer as this. And cos of negative 330, we would get the same answer as this, etc. So you can also define theta to be negative here. Similarly here, we could, as well as taking theta to be positive 120 here, we could have defined theta to be equal to negative 240. And if we had worked at any of the functions there, like sine of negative 240, we would have indeed got the same answer. And we could do the same thing here. This would have been defined as negative 135 degrees. We could have done that. Or this here would have simply been negative 30 degrees. And I urge you just to check in your calculator that sine of negative 30 is indeed minus a half, cos of negative 30 is indeed root 3 over 2, and tan of negative 30 is indeed negative root 3 over 3. So we've extended the definitions of sine, cosine and tangent to angles beyond 90 degrees, and in fact anywhere, any angle, positive all the way around to 360 or negative all the way around to negative 360 and beyond. So we have extended the definitions there. Okay, so next, imagine that we allowed this point to go round the circle and we recorded what theta value matched what sine theta value, and we plotted them on a graph. So what theta value, so say for example, here's one here, that theta there was 330 or minus 30, and it got us the sine value of minus a half. So we would plot 330 against minus a half. And say over here, somewhere over here, if that was a 30 degrees here, and we know that we would plot 30 degrees against a half here. And imagine we plotted those degrees against what the sine theta value was. We would get a sine theta graph, and this is what it would look like. Now I'm going to extend this and build upon this. So copy this graph down. You must know this graph. And you must also know something from Core 2, that pi radians is got a C sign, is the same thing as 180 degrees. So I'm going to interchangeably use pi radians and 180 degrees when dealing with trigonometric functions. So I have to have my sine graph. I'm going to learn it between negative 2 pi and 2 pi. This point here is clearly pi by 2. It's halfway between. This point here is 3 pi by 2. This point here is negative pi by 2. This point here is negative 3 pi by 2. Okay, what degrees values do they correspond to? Well, 0 is 0, pi by 2 must be 90, pi is 180 by definition, 3 pi by 2 must be 270, 2 pi must be 360, and similarly the other side but negative. So these are the degrees. So you must be able to draw this graph either in degrees or radians. At maximum, the sine graph reaches the value 1, and at minimum, the sine graph reaches the value negative 1. It never gets beyond that. And that is effectively our sine graph. That is if we plotted every angle as we go around the unit circle against what I got for the value of sine theta for that angle, and I get something like this. Now I've already stated these, but the maximum value of sine theta is 1. So sine theta at its maximum is 1. It's always less than or equal to 1. The minimum it could be, well, sine theta is always bigger than or equal to -1. The minimum is a place like that, the maximum is a place like that. It's always, sine theta in fact, is always in between 1 and -1. Where are the roots? Well, the roots are here, 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 and here. They're the x values where you get, they're the theta values where you get sine theta is 0. So the roots in radians are looking to be minus 2 pi, minus pi, 0, pi, and 2 pi. And you could state that in an easier way as n pi, where n is an integer, some integer. And in terms of degrees, well, it's going to be equal to 180, n times 180 degrees, where again n is an integer. And the period, how long does it take to repeat itself? How long does it take you to get from this point here till you start repeating the exact same thing? So here, you've just come up to a peak and you're going down. Well, here, you're just coming up to peak and you're going down. It's taken you here 2 pi to get there. Or it might be easier to see from here. You're coming up to a 0 and you're going above the 0. Well, here you're coming up to a 0 and you're going to go above after, so it's taken 2 pi. So the period is 2 pi, and that's equivalent to 360 degrees. So 2 pi radians, or 360 degrees. You need to know the graph of the sine theta like you know your own reflection. We're going to solve all the problems using that graph, whether it be in radians or in degrees. Similarly, if you plot theta against cosine theta, you get the following graph. You'll notice it's like cos theta, apart from you might say it's shifted to the left by pi by 2. So we're going to put in all the same points here. This point here is pi by 2. This point here is 3 pi by 2. This point here is minus pi by 2 and minus 3 pi by 2 here. Similarly, the degrees must be 0, 90, 180, 270, 360, minus 90, minus 180, minus 270, and minus 360. The maximum value here is at 1. The minimum value here is at -1. So the max of cos theta, again, cos theta at its max, but it's always less than or equal to 1. Cos theta is always bigger than or equal to -1. So as with sine theta, cos theta lies between 1 and -1. The roots are here, 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 and here. So minus 3 pi by 2, minus pi by 2, pi by 2, and 3 pi by 2. You could say the odd multiples of half pi. So you could say that is at 2n plus 1 pi over 2, because each of these are an odd number. The next one would be 5 pi over 2. So if n is 0 here, you get pi by 2. If n is 1, you get 3 pi by 2. If n is minus a half, you get minus a half, where n, again, is an integer. And you could do the same thing with 180. I'd just swap the pi with 180 in my definition. And the period, as before, is 2 pi or 360. When am I coming up to a peak and then just about to come down again? At this point here, and that's 2 pi or 360 degrees. And lastly, you need to know the graph of tan theta. Tan theta looks like this. There are some key points of tan theta and key definitions you need to know. I'm just going to draw something in there that I'm going to refer to in a second. This here would be at pi by 2. This here would be at 3 pi by 2, minus pi by 2, minus 3 pi by 2. And if we draw in the degrees just for our sake, 0, 90, 180, 270, 360, minus 90, minus 180, minus 270, minus 360. Now, the graph here, the maximum value of the graph actually shoots off towards infinity at pi by 2 and 3 pi by 2, minus pi by 2 and minus 3 pi by 2. It doesn't have a maximum. Similarly, it doesn't have a minimum. It shoots off to negative infinity. So these aren't really appropriate. What it does have, it has asymptotes, what's called an asymptote. There is an asymptote at these values here. Minus 3 pi by 2, minus pi by 2, pi by 2, and 3 pi by 2. I.e., as we did before, 2n plus 1 over 2 pi for n, an integer. Every odd number over 2 multiple of pi gives us an asymptote, a place where the graph shoots off to infinity and shoots down to negative infinity. The roots, well, the roots here, you can see them here. They're the whole number integers of pi, so they're n pi, where n is an integer, or 180 n, where n is an integer. And the period, it repeats itself every pi, or 180 degrees. So it has a slightly different period. It's half the period of the other two. You need to know those graphs extremely well in order to be able to do all the questions we're about to do. Okay, the next thing you need to be able to know, and you had to know this for the purposes of your AS, you had to know various results for sine theta, cos theta, and tan theta for various degrees. Okay, and I'm going to fill these out for you. I'd suggest you copy these down. It's more handy if you learn these. Obviously, you're going to have a calculator in core 3, but these really should be in your head. Now, firstly, you know we said that pi was the same as 180 degrees. So pi radians is the same as 180 degrees. So you need to know the values of sine, cos, and tan for these degrees. What are the radians of these? Well, that's clearly 0 radians. 30 degrees would be pi by 6 radians. 45 degrees would be pi by 4 radians. 60 degrees would be pi by 3 radians. And 90 degrees is the same as pi by 2 radians. Now, sine of 0 is equal to 0. Sine of 30 is equal to a half. Sine of 45 is equal to 1 over root 2. Or if you rationalise it, root 2 over 2. Sine of 60 is root 3 over 2. And sine of 90 is 1. Let's just check that looks right on our sine graph. For example, sine 30 being a half. Going back here, sine of 30 degrees would be somewhere like here. It does look like it's a half. Okay, so it's making some sort of sense. Cos of 0 is equal to 1. Cos of 30 is equal to root 3 over 2. Cos of 45 is 1 over root 2. Or if you rationalise it, root 2 over 2. Cos of 60 or pi by 3 radians is equal to a half, and cos of 90 is equal to 0. And tan, lastly, tan of 0 is equal to 0. Tan of 30 is equal to 1 over root 3, or if you rationalise it, root 3 over 3. Tan of 45 is 1. Tan of 60 is equal to root 3. And tan of 90 is undefined. Let's just look at the tan graph. Does that make sense? Tan of 0 is 0. Tan of 0 is indeed 0. Tan of 45 is 1. Does that look right? Tan of 45, yep, that looks to be 1 there. Agreed. Tan of 90 is infinite. Yeah, tan of pi by 2 or 90 is indeed infinite. So do commit this particular table to memory. You do have a calculator in the exam, but it makes it much easier if you know these. Okay, let's move on and actually use these things. This is a typical question from Core 2. Express the following trigonometric ratios of either 30 degrees, 45 degrees, and 60 degrees as trigonometric ratios of these, and express their exact values. Now, you're going to use graphs for this. I'm always going to use graphs in order to answer any trigonometric question pretty much. So sine graph started at 0, came down at 180, came back up at 360, and probably came back down over there, you would say at 540 over here. So 420 is going to be somewhere here. 420 is 60 along from here, 60 degrees along from here. So what is the value of sine 40 in terms of something we know? Well, that must have the value the same as the following. That has a value the same as here and the same as here. But we might know that one. This is 60 from the point where we cross the axis. So this here must be 60 away from the root. So this must have the same value as sine 60 degrees, which we know to be equal to root 3 over 2. And indeed, if you check your calculator and it's in degrees mode and you type sine of 420, you get root 3 over 2. Cos of minus or negative 210, again, draw a graph. I'm always drawing graphs with these questions. What did cos look like? It started up here, came down for 90, and that was 180. Then it was 270, and finally it came up for 360, and it was the same the other side here. This was minus 90, minus 180, minus 270, and this would have been minus 360. So where's minus 210 here? Well, let's circle it. Minus 210 is somewhere here, and it's 60 degrees back from the negative 270. So we're going to draw a line across here and see where we get a similar value to this. Well, just by looking at this, there is no similar value between 0 and 90. But what we can say is we can use some symmetries of the graph. We can say this is 60 away from a root, okay, and it has whatever value here. So if we, let's say, come 60 away from that root, so let's go 60 away from that root, so we go 30. This value here is going to have the same number as that value there, apart from that's positive and that's negative. So this cos of negative 210 will be the negative, making this negative cos of 30. And cos of 30 is root 3 over 2, so this would be negative root 3 over 2. And if indeed we type in our calculator cos of negative 210, we do indeed get negative root 3 over 2. So what we had to do here is we had to say this was 60 back from a root, and it brought it down there. If we come 60 back from this root, this must be equal to this, apart from this is positive, and this is the same number, but it's negative. Hence, we can use that symmetrical property there. And tan of 300, let's draw the graph, tan of 300. Be careful with tan's probably the hardest one to draw. 90 here, minus 90 here, goes up like this. That would have been the point here, 180. It goes up to 270 here. Starts at 270 and ends at 360 here. So what's tan of 300? Well, what we're going to do is we're going to say tan of 300 is somewhere here. It's 60 back from 360, that there. We're going to draw a line for ourselves. Now, there's nowhere where this crosses between 0 and 90, so there's nothing we can do other than we can say, look, this is 60 back from a root, so it must have the same value as being 60 forward from that root, given the symmetry of tan, apart from, again, this is a positive answer, but we want a negative answer. So we know that tan of 60, this is going to be the negative of tan of 60. We know tan of 60 is root 3, so this is going to be negative root 3. And indeed, if you type in your calculator tan 300, you get negative root 3. Okay, there's a few for you to do. Pause the video here, have a go at the following, double check. You can leave your answer as an exact surd using either 30, 45 or 60 degree trigonometric ratios. Pause the video, in 5 seconds I'll show you the answer. Okay, here are the answers. I'm not going to go through these, I'm just going to put them up there. They're for you to make sure you can do. You have practiced this in Core 2, this is for you to make sure you can do, and you must use graph method the way I've been using there to do that. Okay, moving on now. We have to be able to sketch transformed trigonometric graphs. Okay, and I'm going to just do various examples. The way I encourage you to do these is because you've done Core 2 before, pause the video, try each question and double check you understand my explanation and you get it right with what I do afterwards. So if you want, pause the video, have a go, but at this point I'm going to go through. Now, the sine theta graph, whenever I'm trying to draw these, I always start off with the sine theta graph. The sine theta graph between 0 and 360 looks like that. That's y equals sine, or y equals sine x, for example. Between 0 and 360 goes between 1 and -1, and this point here is 180, this point here is 360. Always sketch those out, and y is 3 sine x is the same graph, but it's been stretched by a factor of 3 in the y direction. So this one here, if I was drawing a sketch of it, what I would do is it's a sketch again, as long as you label it, I would have it something like this. And this point here is 3, this point here I would label as -3, and again make sure you label key points here, that being 180 and that being 360 degrees. And you're done. Example 2, pause the video, have a go. I'm going through in 5 seconds. Okay, the tan graph between -pi and pi is between -180 and 180. So the tan graph, remember, looks something like this. This here would be pi by 2. This, which is 90, this would be -pi by 2. And here you'd have something that looks like that. And that here would be pi. And over here you'd have something that looks like that. And that would be pi. So there's your y equals tan theta graph, this being theta, this being y. And now what you've got to do is transform it by multiplying it by -1. Well, multiplying it by -1, all it is it makes it a reflection in the x-axis, or the theta axis here. So this graph here would then look something like the follows. Be careful with tan, it's a hard one to draw. I'll draw it in a different colour here. At this point here, that was massively big number. Now it's going to be a massively small number. This here is massively small, so it's going to be massively big. It's going to look something like that. This here as well. It's going to look something like that. And this here is going to look something like that. So this here would be pi, minus pi even, that should be minus pi by 2, pi by 2, and pi. So all I've done there is reflected this in the x-axis there, or the theta axis, and that is that transformation. Here's another one. Pause the video, have a go if you feel you can. I'm going through in 5 seconds. Well, as always, you're going between 0 and 2 pi. I'm just going to draw out the sine theta graph. The sine theta graph looks something like that. That's pi. That's 2 pi. That's 1. And that's -1. Let's draw out this new graph here. I'm just going to draw the axes. Remember, really what you've done here, this is the same as sine x minus 1. All you've done here is you've shifted the graph down in the y direction by -1 units. Okay, So this point here was at 1, let's say. This point now is going to be at 0. This point was at 0. It's going to be at -1. This point was at 0. It's going to be at -1. This point was at 0. And it's going to be at -1. And this point was at -1. So it's going to be at -2 now. So all you've done here is you've shifted the graph as so. And you should put in your key points there. That is going to be pi by 2. That's going to be pi. That's going to be 3 pi by 2. And that's going to be 2 pi. Next one. Pause the video, have a go. Well, you should know the cos graph between 0 and 360 starts here. That was going to be pi by 2. That there is going to be 3 pi by 2. Sorry, pi even. That there is 3 pi by 2. And that there is 2 pi. And all you're doing here, this adding a half, well, that's effectively just cos theta plus a half. You are shifting the cos theta graph up by a unit of a half in the y direction. So if you draw the graph, it would be exactly like this one here. That's 1 there. It's now going to be 3 over 2. That there was 0, so it's going to be a half. That's going to be a half. That's going to be here. It's going to be there. So it would look something like this. Bit betterly drawn than that maybe, but something like that. Again with key points labelled. This is going to be pi by 2, pi, 3 pi by 2, and 2 pi, and 0. Or even with, you were supposed to be with 360, I need to be careful here. That was supposed to be 90, 180, 270, and 360. And similarly here, you must get the degrees or radians, whichever they ask for, correct. Next one. Okay, the tan graph here, they want it between 0 and 2 pi. Remember what the tan graph looks like. It looks something like this. That's going to be pi by 2. That's going to be equal to pi. And that's 3 pi by 2, that asymptote there. And this one's going to come up here to finish off at 2 pi. So that's the original y equals tan graph. Now there's what's happening here is this graph, you're adding pi by 2 inside the brackets here, inside the function. This results in a shift to the left of minus pi by 4. So if we draw our graph here, we'll be careful doing this one, it's a bit more complicated. It crossed here at pi, and it's now, sorry, the asymptote, for example, was at pi by 2. Now it's going to be at pi by 4. So that's the asymptote, at pi by 4. It crossed at pi, now it's going to cross at 3 pi by 4. It had an asymptote here, it crossed again at 2 pi, now it's going to cross at 7 pi by 8. So we're going to have something that looks a bit like this. And you're going to have yourself coming up a bit. And here you're also going to get a portion of the graph coming through here that would look a bit like as so. Okay, and that point there is going to be when theta is 0, and that's tan of pi by 4, which is the point 0, 1. So it's important to label that on there as well. This here would be 2 pi here, and that would have the exact, that would actually have, should have the same value as this here. This should have the value 1 here at that point. Okay, we're going to do a few more now. want to draw that graph as sine of 2x, just for my own benefit, draw the graph of sine 2x between 0 and 360. I'm getting quick at these, looks like this. Goes between 1 and minus 1. Sine of 2x, or 2x inside the function, actually squashes the function by a factor of 2. So squashes the function in the x direction. So it squashes it inwards by a factor of 2. So if I drew that here, okay, it's going to cross not at 180 now, but at 90, not at 360 now, but at 180. So it's going to come up to 1 and down quickly. It's going to come back up, and then also we're going to get another set in there. We're going to come up and down to 270, and we're going to come up and down at 360 here. And there we go, the key points there, that is y equals sine of 2x. Next one, have a go at this, cos of theta over 3 between negative 3 pi and 3 pi. Firstly, I draw cos of theta. I would just, there we go, that's going to be pi by 2. It's going to be pi. Be 3 pi by 2. It's going to be 2 pi. It's going to come down there. It's going to be 5 pi by 2. It's going to come over there. It's going to be 3 pi. You're going to get a similar thing the other side, which I'm just going to do much quicker. So, okay. And so this particular graph here, what's this transformation doing? Well, the dividing by 3 inside the cos function is actually stretching it in the x direction by a factor of 3. So where you cross that pi by 2, you're now going to cross that 3 pi by 2, which is over here. Where you crossed here at 3 pi by 2, you're going to cross that 9 pi by 2, which is outside the range. What is still in the range? So this here looks something like this. And this here looks something like this here. And that's supposed to be 3 pi over 2 and minus 3 pi over 2. And this point here was at 2 pi here. Sorry, this was our next point. This point here is at pi when you hit the bottom, so it's going to be at 3 pi now where you hit the bottom. Similarly here, this point here should be minus 3 pi. What you've done is you've stretched out this by a factor of 3. That is now 3 pi by 2, that is minus 3 pi by 2, that is now 3 pi, that is now minus 3 pi. And lastly, this one, have a go, pause the video, have a go, otherwise double check you got the right answers. The tan graph now, we should be familiar with the tan graph. That's our asymptote there. So this here was 0, 180, 360, minus 180, minus 360. And tan of minus x, well, the negative x inside the bracket, all it does is it's a reflection in the y-axis. So I'm just going to actually draw this on the same one. This one here is going to look something like this. And this one here. Okay, so it should look something as follows. And this one here was tan of minus x. Okay, two important trig identities you need to know from Core 2. Sine squared theta plus cos squared theta is identical to 1, and tan theta is identical to sine theta over cos theta, with a certain provision that cos theta cannot equal 0. Otherwise you'd be divided by 0, and you can't do that. Right, let's use these identities. Here's an example, typical question. Simplify the following. Well, you know sine squared of any angle plus cos squared of the same angle is equal to 1. So this is obviously 1, because it doesn't matter that it's 3 theta in there. It could be x, y, z, anything. Sine squared of an angle plus cos squared of the same angle is always identical to 1. 5 minus 5 sine squared. Well, that, if I factorise out the 5, factorising is such an important skill. 1 minus sine squared theta, and 1 minus sine squared theta using this here would be equal to cos squared theta. So that's 5 cos squared theta. I should have just actually said back here, this here, the two extensions of this are, you get that sine, you get the following. You get that 1 minus cos squared theta is therefore sine squared theta, and similarly 1 minus sine squared theta is cos squared theta. Two things you use a fair bit, and that's what we've used here. And this one here, sine of 2 theta over 1 minus square root of 1 minus sine squared 2 theta. Well, that's just sine 2 theta over the square root of, well, 1 minus sine squared 2 theta must be cos squared 2 theta, and this therefore must be equal to sine 2 theta over the square root of cos squared 2 theta, which is cos 2 theta, and sine 2 theta over cos 2 theta is tan 2 theta. And we're done. So we've used the trigonometric identities to simplify expressions. The examiner then wanted us to show our own identities, new identities, and here's example 2. The way we would show this. Maybe have a go if you think you can do it. Otherwise, double check that you understand how to do it. You start with one of the sides and show it's equal to the other. So I'm going to start with the left hand side, and I'm going to write it out. Cos 4 theta minus sine 4 theta over cos squared theta. I'm going to play around with the algebra with this and try and show it's equal to the right hand side. That's a difference of two squares. It's cos squared theta plus sine squared theta, cos squared theta minus sine squared theta, all over cos squared theta. Well, cos squared theta plus sine squared theta is 1 from up here, so this must be cos squared theta minus sine squared theta, all of that, each bit divided by cos squared theta. In particular, I can divide the first thing by cos squared theta and get 1, and sine squared divided by cos squared is tan squared theta, and now we have equal to the right hand side, and we've done. So we can use these two identities to prove further identities, which is a common core 2 question. And lastly, a common core 2 question, something like this. Cos theta is negative 3 over 5, theta is reflex, find sine theta and tan theta. Well, sine theta, let's use this here. We know that sine squared theta, not sine theta, but sine squared theta is 1 minus cos squared theta, which is 1 minus 3 over 5 squared, which is 1 minus 9 over 25, which is 16 over 25. Okay, so sine theta must be the square root of that, which is plus or minus 4 over 5 if I take the square roots. Now, which is it, plus or minus? Well, I'm going to go to graphs here. Theta is reflex, so that means theta, to be reflex, theta is between 270 and 180, isn't it? It's over 180, it's a reflex angle. So the sine theta graph looks something like this. Okay, and where is it equal to where's the sine theta? Which is it going to be, 4 over 5 or minus 4 over 5 if it's reflex? If it's reflex, it's going to be bigger than 180, so it's certainly going to be a minus number. So sine theta in this case can't be the positive 4 over 5, it must be the negative 4 over 5. Okay, and then tan theta, I'm just going to rub this out and do tan theta beside it so I don't have to go into another page, doing a different colour pen. What's tan theta? Well, tan theta is simple. Tan theta is sine theta over cos theta for the particular sine and cos we've got. So it's minus 4/5 divided by minus 3/5, which is going to be equal to 4 over 3. And we're done. And the last thing we've got to be able to do with all this trigonometric, so we're nearly there, we've probably got another 10 minutes to go, is solve trigonometric equations. I'm going to do various examples, always using a graph. Try each one on your own first, because you should know this from Core 2. So pause the video, try, and then double check you're getting the same answer as me. We're trying to solve sine theta as a half in between 0 and 360. Okay, first thing you do is so you're trying to solve sine theta is equal to a half. You find what's called the principal value by doing the inverse sine of a half on your calculator, and you get that is equal to 30 degrees. You then straight away draw your graph and you go in between 0 and 360. We know cos looks, sine even looks something like this: 0, 180, 360. And your principal value, which you're going to draw in, is here at 30 degrees. So you're going to draw a line up here, and you're going to go across here, and you're going to find where else is sine the same. Well, sine is also the same here, and this point here is 30 away from the 0, so this is going to be 30 back from the 0, it's going to be at 150. So theta, there are two answers for this. In between 0 and 360, theta on the one hand is 30 degrees, on the other hand is 150 degrees. Okay, next example, pause the video, have a go. Right, going through, we're trying to solve 5 sine x equals negative 2 between 0 and 360. So, first of all, rearrange so sine x is the subject, divide by 5, minus 2/5. Find your principal value of x by taking the inverse sine of minus 2/5 or minus 0.4. So work that on your calculator, inverse sine, negative 0.4, and you should get x is equal to negative 23.58 degrees, let's say to 2 decimal places. Draw your graph out, and your sine between 0 and 360 looks as so. Just extend it back a little bit for the sake of your principal value. It's at minus 23 degrees here, minus 23.58. Where will you have a similar value to that? Well, you will have a similar value at all these points here. So we are 23 degrees back from a root here, so we're going to be 23 degrees that way from a root and 23 degrees that way from a root. That root's at 180, that root's at 360. So therefore, x is going to be 180 plus 23.58 degrees, and it's going to be 360 minus 23.58 degrees. So we're going to get for that 180 plus 23.58, we're going to get 203.58 degrees, and we're going to get 336.42 degrees. And there we go, example 2 done. We're trying to solve this here. So we're trying to solve cos of x is equal to root 3 over 2. Straight away work out the principal value by taking the inverse cos of root 3 over 2, and for that you get yourself 30 degrees. Then you're going to draw your cos graph. you're going between 0 and 360. So this here is 90, 180, 270, and 360. Your principal value is 30. So you're along here, that's 30 there. And you're going to see where else you get a similar value to that. Well, it's over here somewhere. Now you're 30 back from a peak, so this one here must be 30 back from this peak, which is at 330. So x on the one hand equals 30 degrees, and on the other hand is 330 degrees. And that's another one done. Example 4. Find the values of theta in radians in between 0 and 2 pi that satisfy the following. So we're trying to solve sine theta is root 3 cos theta. Well, assuming cos theta is not 0, so assuming cos theta is not equal to 0, we can divide by cos theta and get tan theta is equal to root 3. Dividing both sides by cos theta, because that would be sine over cos, which is tan, and this would be cos over cos, which is 1. Find the principal value, would be inverse tan of root 3. And that's 60 degrees, but in radians, that's pi by 3. Okay, time to draw a graph out here. As always, you're going between 0 and 2 pi. So this here goes up here, pi by 2. Pi, 3 pi by 2, that's here at 2 pi. So pi by 3 was our key principal value, so pi by 3 is somewhere here, it's pi by 3, and we want to work out the other values that are pi by 3. Well, that's pi by 3 from a root, so this must be pi by 3 from this root at pi, so it'd be 4 pi by 3. So theta must be pi over 3 and 4 pi over 3. And that's it. You've got your two roots in between your right interval. And we've done another one. Example 5. Solve the equation cos 3 theta is 0.7666. Well, cos 3 theta complicates the matters. So what I'm going to do is I'm going to do a substitution, and I'm going to let x, capital X, be 3 theta. If theta was between 0 and 360, then 3 theta, which is x, must be between 0 and 3 times 360, which is 1080. So I'm going to have to extend my range when I make this substitution. So I'm trying to solve cos x is equal to 0.766. Okay, find my principal value of x is the inverse cos of 0.766. Inverse cos of 0.766 is about 40 degrees to 2 decimal places. For our cos graph, I'm going to go from 0 all the way to 1080, so it's going to be, I'm going to have to do it very small and carefully. This here is 90, 180, 270, 360, 450, 540, we'll run out of space a bit here, 630, 720, 810, 900, 990, just got it, and 1080. This should be 1080. And I've extended the range. My principal value was theta is 40, somewhere here, which is 40 from the peak. So draw a nice little line all the way along. There's going to be many places where we're going to get a value. X is therefore going to be equal to 40. 40 from the peak, 40 back from the peak, 320, 40 that way from the peak, 400, 40 back from the peak, 680, 40 forward from the peak, 760, and 40 back from the peak, which is 1040. But you want to solve for theta, and this was 3 theta, so theta must be all of this divided by 3, which is 40 over 3, 320 over 3, 400 over 3, 680 over 3, 760 over 3, and 1040 over 3. And you have found all your answers. Okay, we'll try another one. Again, pause the video. Pause the video there if you think you can do it, and we'll go through. I'm going to make a substitution. I'm going to let x be 2 theta minus 35, so that my particular range, if my range is now 2 theta minus 35, I double each side, subtract 35, that's going to be between 325, and that's going to be between minus 395. And what I'm trying to solve is sine of capital X is equal to negative 1. So capital X must be the inverse sine of negative 1, which if you work out on your calculator, you're going to get minus 90 degrees. So we're going to draw out our graph for that. But this time we've got to be careful to extend our graph for sine X a little bit. So sine X goes like this here, and sine X would go back here like this. We want to continue it another, if that's minus 360, we want to continue it another bit here to minus 395, and we wanted to really stop it at 325, which we might say is somewhere like here. That should be 325. And our principal value was negative 90, so negative 90 is here. Negative 90 degrees there. What other values have got the same? Well, let's draw a line across. It's only going to be at this point here, which is 2 pi along, or 100, pi along. So that's pi, that's 90, another 90, another 90, another 90. It's 360 along. So theta is going to be minus 90 and 270. And so 2 theta minus 35, that's 2 theta minus 35 is minus 90, and 2 theta minus 35 is 270. So solving for theta, add 35 and divide by 2. You get minus 27.5 degrees. And you get theta is 152.5 degrees. And you're done. There are the two answers. Trying to solve this equation here. These are actually quadratics in disguise. They're quadratics with trigonometric functions inside them. So we try and solve a quadratic first of all by factorising if we can. And we could factorise that to cos 2 theta cos theta minus 1 plus 1 is equal to 0. So we get two sets of potential solutions. Cos theta on the one hand is equal to, well, let's not jump a step. Let's just say 2 cos theta plus 1 is equal to 0, or cos theta minus 1 equals 0. So therefore cos theta is equal to minus a half, or cos theta is equal to 1, and we're between 0 and 360 as always, and we always do this. Let's draw our graph out between 0 and 360 in this case. Okay, 90, 180, 270 and 360. So we want where cos theta is minus a half. Well, cos theta equal to minus a half is going to be here somewhere. We could find the principal value of that. That would be theta. If you inverse cos minus a half, if you take the inverse cos of minus 0.5, you get 120. So this 120 is there, it's 30 away from that point. So this one here should be 30 back from that point at 240. So theta is 120 and 240. And where is theta 1? Well, it's at 1 at 0 and it's 1 at 360. So our answers for theta in order are 0, 120, 240 and 360. And our last example, I'm sure you'll be glad to hear, the very last one, and we have revised everything in Core 2 trigonometry. Find the values of x between minus pi and pi, satisfying that equation there. So we are trying to solve 2 cos squared x plus 9 sine x equals 3 sine squared x. Okay, you'll notice there's cos squared x's, sine x and sine squared x's. It would be better if everything was in terms of one of them, preferably sine x's, because we've got a sine squared and a sine. We can convert this, because we know from our identities that cos squared x is 1 minus sine squared x. So we can substitute that in. 2 1 minus sine squared x plus 9 sine squared x must equal 3 sine squared x. Expanding out, you get 2 minus 2 sine squared x plus 9 sine x equals 3 sine squared x. We're looking like we're going to have a quadratic in disguise with sine squared x and sine x's, so I'm going to subtract 2 off both sides, add 2 sine squared x to both sides and minus 9 sine x, i.e. make this side 0, and I would get 5 sine squared x minus 9 sine x minus 2. It's a quadratic, we'll give it a go at factorising, see if we can do it. It must be 5 sine x, must be minus 2 plus 1, and therefore sine x must be minus a fifth, or sine x must be 2. Now you could ignore this one because you know sine is always between 1 and minus 1. It can never be bigger than that. So we continue with this one. You take the inverse sine on your calculator. So take the inverse sine of minus a fifth, or minus 0.2. Remember your calculator needs to be in radians mode because you're dealing with radians. The principal value, the inverse sine, so the inverse sine of negative a fifth is minus 0.20 radians. So in order to find the other ones, let's just, as always, draw our graph. Going from minus pi up to pi. So as follows, minus 2 radians is going to be somewhere like here. So the other one is obviously going to be over here. So we're 0.2 away from that 0, so we're 0.2 back from that 0. So the other one's going to be pi minus 0.2. So our two values are x is minus 0.2 radians, and our other value is going to be, it's minus pi plus 0.2. You're at minus pi here, and you go 0.2 from that. So we're going to be minus 2.94 radians. And that is our final answer to this problem. And I hope you found the following. That's everything now on trigonometry from Core 2. So I hope you found that useful in your revision and preparation for Core 3 trigonometry. Thanks for watching. Do tune in next time.